You're familiar with the rule for multiplying complex numbers. Now, you'll explore a theorem that was discovered 300 years ago by a French mathematician. The theorem describes a convenient rule for determining powers of complex numbers. Recall the multiplication rule, which is z1 times z2 is equal to r1 times r2 times the quantity cosine of theta 1 plus theta 2 plus I times the sine of theta 1 plus theta 2. How can this formula be used to find the square of a complex number? Instead of multiplying two different complex numbers, consider what happens when a single complex number gets multiplied by itself. If z1 is equal to z2, then we could just represent it with z. And then if we want to evaluate z squared, we would just rewrite it as z times z. Since the modulus, or r values, would be identical, we can write them both as r. This would be the same for the arguments, or angle theta, as well. We can write both angles as theta since they're identical. The multiplication rule gives us r times the quantity of cosine of theta plus I times the sine of theta plus theta. Simplifying this expression, we get r squared times the quantity cosine of 2 times theta plus I times the sine of 2 times theta. And how can this formula be used to find the cube of a complex number? Take the result from squaring the complex number and multiply that result by the original complex number. So z cubed is equal to z squared times z. The modulus values would be r squared and r. The arguments, or angles, would be 2 theta and theta. So the multiplication rule gives us r squared times r times the quantity of cosine of 2 theta plus I times the sine of 2 theta plus theta. Simplifying that expression, we get r cubed is times the quantity cosine of 3 times theta plus I times the sine of 3 times theta. Now it's time to generalize these results into a formula for a complex number raised to any integer power. If we look at the results from the previous calculations, we can make a generalization of the rule for raising a number to the power n. If we look at the exponent for each multiplication, it is also the exponent for r as well as the value that theta is being multiplied by. Generalizing this gives us z to the nth power is equal to r to the nth power times the quantity cosine of n times theta plus I times the sine of n times theta. This is de Moivre's theorem, discovered in the early 1700s by Abraham de Moivre, a French mathematician. The rule for raising a number to the power n is to raise the modulus to the power n and multiply the arguments by n. The image on the right displays complex number z along with two different powers of z. The original complex number has a modulus greater than 1, meaning the modulus value will increase when raised to successive powers. As you look at the numbers z squared and z cubed, you'll see the distance from the number to the pole is increasing. Had the modulus of z been less than 1, the numbers z squared and z cubed would have moved closer to the pole instead of farther from it. The arguments are also increasing, but by multiplication instead of powers. The increasing arguments result in this counterclockwise rotation, as seen in this image. Now to practice what you've learned. De Moivre's theorem is definitely useful, but what guarantees its results are correct? It's one thing to see that it works for squaring or cubing a complex number, but does it work for all positive integer powers? To answer this question, a proof by mathematical induction is needed. In order to prove a theorem is true for positive integers represented by n, the first step is to show that it works when n is equal to 1. Thus, this first step is to verify that the theorem is true when n equals 1. The next part of an induction proof is to prove that it works for all greater integers. This is done by first supposing that the theorem works for some unspecified integer represented here by k. Thus, the second step is to assume that the theorem will be true when n is equal to k. And finally, the theorem must be proved when k, whatever it may be, is incremented by 1. Thus, the third step is to prove the theorem to be true when n is equal to k plus 1. Now it's time to apply this reasoning to De Moivre's theorem. Okay, time to apply mathematical induction to De Moivre's theorem. This analysis will look at the trigonometric portion of a complex number. Those are the terms containing cosine and sine. What about the value of r? Well, the application of induction to the r value is very straightforward, based on the properties of exponents. So this proof will focus on the trigonometric portion of the complex number. The first step is to verify the theorem is true when n is equal to 1. This will mean verifying the equation that the cosine of theta plus I times the sine of theta raised to the first power is equal to the cosine of 1 times theta plus I times the sine of 1 times theta. It's clear that both sides of the equation are the same, so the verification is successful. The second step is to assume the theorem to be true when n is equal to k. The theorem is expressed as the cosine of theta plus I times the sine of theta raised to the power of k will equal the cosine of k times theta plus I times the sine of k times theta. And this statement is assumed to be true. The third step is to prove the theorem to be true when n is equal to k plus 1. In other words, the statement cosine of theta plus I times the sine of theta raised to the power of k plus 1 is equal to the cosine of k plus 1 times theta plus I times the sine of k plus 1 times theta. And this must be shown to be true. Now to proceed with the proof of this last statement. The final step is to prove that the cosine of theta plus I times the sine of theta raised to the power of k plus 1 is equal to the cosine of k plus 1 times theta plus I times the sine of k plus 1 times theta. Begin by expanding the left side of the statement, using the power of a product property for exponents. Remember, when the bases are the same, we add exponents. So if we use this power in reverse, we rewrite the expression as multiplication, separating the k and the 1. The first expression in the brackets was part of the assumption that was made. This was the n is equal to k step. This first expression, the cosine of theta plus the I times the sine of theta raised to the power of k, is substituted with an equivalent expression. That expression can be substituted with the cosine of k times theta plus I times the sine of k times theta. And then we'll multiply the same cosine of theta plus I times the sine of theta. Next, apply the distributive property to multiply the pair of binomials. So we are going to multiply these two values together to get this one, and these two values together to get this one, and these two values together to get this one, and these two values together to get this one. Remember that I squared is equal to -1. And so we can rewrite the terms, putting the two real terms together and the two imaginary terms together. Each expression in brackets is actually a trigonometric sum identity. Using the cosine sum identity, we can replace the cosine of k times theta times the cosine of theta minus the sine of k times theta times the sine of theta with the cosine of k times theta plus theta. And using the sine sum identity, we can replace the sine of k times theta times the cosine of theta plus the cosine of k times theta times the sine of theta with the sine of k times theta plus theta. The last step is to factor the theta from each of the arguments. And notice that this result matches the statement at the top of the screen here. This means the proof was successful, and De Moivre's theorem is true for all positive integers. Here's an example using De Moivre's theorem to find the fourth power of the complex number the square root of 3 plus I. The first step is to convert the number into polar form by calculating the modulus and argument. The modulus is equal to the square root of a squared plus b squared, which here is equal to the square root of 3 squared plus 1 squared, which equals the square root of 4 or 2. The argument is equal to the inverse tangent of b divided by a, which here is equal to the inverse tangent of 1 divided by the square root of 3, or the inverse tangent of the square root of 3 over 3, which is equal to pi over 6. Thus, the polar form of the number is 2 times the cosine of the pi over 6 plus I times the sine of pi over 6. Now to apply De Moivre's theorem. The modulus of 2 gets raised to the fourth power, which results in 16. The argument of pi over 6 gets multiplied by 4, and the result equals 2 pi over 3. Thus, the fourth power of the original number is equal to 16 times the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3. The image on the right shows both the original number and the fourth power of it. The modulus of z is 2, while the modulus of z to the fourth power is equal to 2 to the fourth power, or 16. This is confirmed by examining the distance from each number to the pole. The argument of z is pi over 6, while the argument of z to the fourth power is 2 pi over 3. Thus, the argument of z got multiplied by 4, which resulted in the counterclockwise rotation shown in the image. It's clear that understanding the geometric representation allows you to quickly compute powers of a complex number. This is certainly easier and faster than trying to multiply the square root of 3 plus I by itself 4 times. Now to practice what you've learned. You have learned De Moivre's theorem for computing powers of complex numbers. Next, you will discover how to reverse the process to determine roots of complex numbers, and you will examine the distribution of these roots around the circumference of a circle. We've seen how De Moivre's theorem can be used to compute powers of a complex number. But what about working in the opposite direction? That is, can a formula be developed to determine the roots of a complex number? Let's take a look. If w to the nth power is equal to z, then w would represent the nth root of the complex number z, and would be the solution to the equation w is equal to the nth root of z. From our geometric understanding of powers of complex numbers, the process can be reversed, so that instead of taking r to the nth power, it will now be taking the nth root of r. And instead of multiplying the argument theta by n, now theta will be divided by n. But the formula isn't quite complete. We need to focus on the trigonometric portion of a complex number. While raising a complex number to a power produced a single result, there are actually multiple roots to a given complex number. This is due to the circular nature of the polar grid, whereby arguments that differ by 2 pi are considered equivalent. Therefore, the cosine of theta plus I times the sine of theta is equal to the cosine of theta plus 2 pi times k plus I times the sine of theta plus 2 pi times k, where k is a non-negative integer. But if equivalent arguments are divided by n, they produce unique arguments that are not equivalent and must be listed separately. These non-equivalent angles represent additional solutions to the problem of determining roots. This property leads to the conclusion that there are multiple roots for any given complex number. 2 square roots, 3 cube roots, 4 fourth roots, and so on. In general, when determining the nth root of a complex number, there will be n solutions to that problem. So we get that w is equal to the nth root of r times the cosine of theta plus 2 pi times k divided by n plus I times sine of theta plus 2 pi times k divided by n. And that will be for values of k from 0 all the way up to n minus 1. For those values, this expression reveals locations of unique roots. Once k reaches or exceeds n, these same locations are repeated and do not need to be listed. Thus, we can stop once k reaches the value of n minus 1. Now, to summarize the results. As you have now seen, the nth roots of a complex number are given by this equation. The value of k ranges from 0 to n minus 1, producing a total of n roots. Any two consecutive roots have arguments that differ by 2 pi divided by n. Thus, the n roots will be equally spaced around the circumference of a circle centered at the pole. The radius of the circle will be equal to the nth root of r, and this image shows how cube roots or fifth roots of a complex number might be positioned around a circle. In these examples, there is a positive real root lying at the polar axis, but that does not necessarily have to occur. It could be that no root lies on the polar axis. Now practice what you've learned. Here's an example using the formula to determine the cube roots of 8. Recall that in the real number system, there's only a single cube root of 8. The cube root is the number 2. This root still exists in the complex number system, but is joined by 2 additional roots, as you'll see. The first step is to express 8 as a complex number in polar form. In the complex number system, 8 is actually equal to 8 plus 0 times I. The polar form would then be 8 times the quantity of the cosine of 0 plus I times the sine of 0. Now to apply the roots formula. To calculate the first root, take the cube root of the modulus and divide the argument by the value of n, which is 3. The value of k is 0, and so the result is 2 times the cosine of 0 plus I times the sine of 0. To calculate the second root, set k equal to 1. This adds 2 pi plus 3 to the argument of the first root, so the result is 2 times the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3. To calculate the third root, set k equal to 2. This adds 2 pi over 3 to the arguments of the second root. This result is 2 times the cosine of 4 pi over 3 plus I times the sine of 4 pi over 3. Notice how the roots are equally spaced around the circle with a radius of 2. Each root has the same modulus, while the arguments differ by 2 pi over 3. The roots of unity are numbers that, when raised to a positive integer power, are equal to 1. They can be calculated using the same formula as before, but they can also be located by understanding their symmetrical arrangement around the unit circle. For roots of unity, the modulus, the value of r, will always be 1, and one of the roots always lies on the positive real axis. The additional roots are spaced equally around the unit circle. For example, there are 2 square roots of 1 shown in the n is equal to 2 circle. The square roots are 1, seen here, and -1, seen here. And there are 3 cube roots of 1 shown in the n equal to 3 circle. The cube roots are 1 here and -1/2 plus I times the square root of 3 over 2, which is here, and -1/2 minus I times the square root of 3 over 2 there.